welcome back. We are discussing the Aldol reaction. So this is the mechanism. You can look into the mechanism. This is a big one. So we are going to study each step one by one. So first of all, we move on to the first step. The first step involves acid base. Now you can also check that this is an hydroxide ion. Hydroxide ion is also having a acid base property, and it can also involve as a nucleophilic property also. So it can act as a very good nucleophile also. So there is a carbonyl center. So hydroxide can attack over here to break the carbonyl oxygen bond, that is the carbonyl carbon oxygen bond, and there will be further reaction. But that is not the story. Rather, we are observing that there is an acid base reaction. So what is the reason for this? To explain this, we need to first of all understand about the energetics of this reaction. Carbonyl carbon, this C double bond O, that has a bond energy of 166 kilocalorie per mole, whereas if you check the bond energy of a carbon oxygen single bond energy, that will be 80 kilocalorie per mole. Obviously the carbonyl carbon bond energy should be double, because an AB bond having single bond A and B, that is a bond energy of X. So A double bond B should have a bond energy of 2x. But here you can see that this carbonyl carbon bond is having more than the double of the bond energy of C single bond O. So obviously it is very much more energy requiring for this hydroxide ion to break this carbon oxygen bond. More energy is required, so it will have a higher energy barrier. So obviously that is not at all a favorable one. So the hydroxide ion goes for an acid base reaction, and there is an ionization. So you can see this is the anion, and this is obviously the water. This is the anion 3A, that is having a resonance to form the enolate. This is the enolate one, 3B. So this is the nucleophilic enolate. Now there is again another story. Why this equilibrium is backward? So for this you need to know some data. Let me give you this particular information about the pK value of water. This is number 4, water. The pK value of water is near about 17.5, 15.7, 15.75 or 15.7, near approximate to that. Whereas for an aldehyde, this aldehyde, it is having a pK value of 20 to 22. 20 to 22. So obviously you can understand, when there is a lower pK value, that is obviously a stronger acid, and the conjugate one is a weaker one. So we are applying this Bronsted acid base concept. Water is having a 15.7 pK. So obviously this is a stronger acid compared to this aldehyde, because aldehyde is having a higher pK. More the pK, lesser the acidity. So water is the strong acid here. So obviously its conjugate base will be weak. So obviously this base is a weak one. This is a weak conjugate base. Whereas the aldehyde is a weak acid. So it will having a strong, this aldehyde is a weak acid, obviously. So this is having a strong conjugate base. You remove this word conjugate. So what is this? This is a weak acid, and this is a weak base, that is having a strong acid and a strong base. In any organic reaction, the equilibrium is driven as the combination of strong acid to strong base to the weak acid to weak base. So obviously it goes to the weaker side. So hence the equilibrium will always be backward. So first step is lagging. Okay, then we move on to the second step. So that will be discussed in the next video. Thank you.